The clock strikes 8. Good morning. How are you guys doing? My name is Professor Niazi. We're going to briefly go over our syllabus today. The Canvas course just got published a few minutes ago, so you haven't been able to access it, but it is published and accessible now. I will be uploading important documents on there with regards to our class. But first, we'll just go over the syllabus briefly and get to lecture because there's a lot of math to cover this semester, okay? Here is our syllabus. You are in Cal 3. As you might know, these classes are being recorded. And as you might have been wondering, what I was doing here was calibrating the scope of the camera because I have to record these lectures just in case one of you guys, I believe I have 4 students, so everybody's here. But let's say one of you guys, is not able to show up for some reason or another, then you can watch every lecture recorded on Canvas. Okay, so we're going to start off from the beginning and have them all recorded. Okay, this portion of the syllabus indicates that, if you're not able to show up to class, we will be having class during normal class times, and you can show up in an online version of yourself. I still don't know how the interface works with online Zoom interaction. I don't know how students will ask me a question if they're just sitting behind the camera watching. I'm gonna have to look at that and see how that works. Yes, ma'am.
There's a chat feature that they might use.
Is that? Yeah, okay. So I have to take a look at that and how that is utilized. I definitely can't have audio where you're like talking to me through there. I mean, maybe that could be a possibility. Maybe we could do that as long as the students adhere to not having too much weird sounds. I'm kind of like a dog, and if I hear a weird sound, I'm like, what is that? So I don't want to have to do that. We'll probably stick to the chat if necessary. All right. Here's my information. My office hours are not decided yet. We'll figure that out later. Course description is a description you will find in the standard SNU catalog. Here's some learning outcomes that you can look at. Here's some of our math department desires for you to be able to extract from this course. We will be utilizing Stewart, 4th edition. And here is some extra text that might be beneficial for you to look at if you require some extra resources. This is how your grade will be determined. These are the following percentages. Quizzes will be given on Fridays, but this Friday I don't believe it will merit a quiz. So starting next Friday, not this Friday, but the Friday after that, we'll get some quizzes flowing. Homework. You will get homework from each section. I'm going to tell you what your homework assignment will be for section 9.1 here in a little bit. Computer labs will be done from 2 to 4. You'll have your own Canvas page dedicated to your labs. That will be with Dr. Zoller, okay? Quizzes, midterms, finals, you can read all these. Academic honesty, response time, whether late work, you might want to check this out. Attendance, SNU really cares about you showing up. Grade appeals, diversity, disability. And as you guys know, you will be reading the syllabus on your own. You have access to this information. Here's our COVID-19 statement. In case you didn't know, that's why we're all wearing masks, except this dude over here. He's drinking coffee. Yeah. Okay. Here's a YouTube channel that I have. It has mathematics how-to tutorials, solve problems and explain concepts. It's an active process, and I'll be putting more calculus information on there. So without further ado, now let's get to our lecture, section 9.1. One last thing that is not on the syllabus that I maybe should include, but is very important to me, is the utilization of technology. If you have cell phones with you right now, I suggest you put them on either silent or vibrate immediately. I'm not okay with students on their phones. I will be respectful towards you, and I demand the same amount of respect back. So cell phones, if you need to answer them, if it's an important call or text from a loved one, or for whatever reasons it's imperative to answer it, please step outside and do so outside. Do not be on your phone. Appreciate that. Our classes are 50 minutes long, and that should be enough to hold your attention span. Okay. Now I'm gonna have this recorded thing. I haven't ever recorded myself live. This is an interesting thing to do. Okay. Right off the bat, I'll tell you what your homework assignment in this chapter is. Your homework will be problems in 9.1, 3, 4, 6, 16, 17, 32, 34, and 39. Those are some nice problems. Okay. So once your homework is due, I believe a grader will be grading your exams, and you'll get some feedback after that. But I aspire to create keys for you. I like to solve all the problems too, just like you guys. And I'll give you some detailed solutions to the homework after it's due. How about that? I don't know how soon I'll get that to you, but I aspire to always be ahead and to be able to give it to you immediately once it's due. Once you turn it in, I'll publish the key, and you'll be able to look at the solutions on how to do the homework for your studying purposes. As the syllabus highlighted that I didn't talk about, but I will now, it is imperative that you do more homework problems than the number that's assigned here for the sake of mastery. Okay. Everything's got to be recorded. So I'm trying to turn off the projector live lecture, and it's not working. So, aha. All right, let's begin. 9.1. Well, in your mathematical journey so far, you've only been talking about things in 2D, 2 dimensions. Okay, so to describe situations in a plane, you know, we have our x-axis, we have our y-axis. Let's say this is some point A, this is some point B. Then this point in space, the coordinate pair A, comma B, requires 2 numbers to locate it. Historically, René Descartes, which came up with the Cartesian coordinate system that we're utilizing right now, saw a bug. Oh, I need to be on that camera. He saw a bug. I like to stroll around and talk, but I can only stroll this much. He saw a bug on a wall and thought, how could I mathematically, rigorously define the location of this bug on this wall? And, well, he thought, well, I can measure how far it is from the wall here, and I can measure how far it is from the ground here, and I can assign 2 numbers, 2 lengths, in the x and in the y, and I can define its location in 2 dimensions. That's exactly what we do when we say this point A, comma B is here in this location. But Calc 3, interestingly enough, the name 3 begs us to utilize 3 dimensions instead of 2. Our real life situations are 3-dimensional. Einstein's theory of general relativity implies that we are actually in 4-dimensional hyperspace time embedded in 5-dimensional hyperspace time, where we have 3 spatial coordinates, the x, the y, and the z. 1 dimension of time, and we're embedded in a higher dimensional space. This is not a course on general relativity. If you want to take general relativity, hit up Dr. Neuenschwander. Dr. Neuenschwander. Okay. I wish I could make this a course into general relativity. But Calc 3 is very cool, and it's just as cool as general relativity. And you need Calc 3 to understand general relativity. So let's give it the respect that it deserves. Now, if I want to move to 3 dimensions, how many numbers will I need? Here I need 2 numbers, 2 links, A and B. How many numbers do you think I would need to describe this point in 3-dimensional space? What?
3.
What?
3.
What?
3.
There we go. Three numbers. So this point, maybe this is some A, this is some B, and now we have some C. And this point in 3-dimensional space is now A, B, and a C. So the description of 3-dimensional space begs us and implores us to just give one more piece of information, that added length in the Z. Okay. So get used to me drawing things like this out. Maybe the dotted lines aren't so helpful because just drawing this stuff on the board is very difficult. But your book has really nice depictions. Also, when I have a ruler at hand, I can make it look kind of nice. But when it's just freestyle on chalkboard, it looks like this. Okay? Just know that we're trying to depict 3 dimensions. There's length, width, and depth. We are introducing depth in Calculus 3. And now we're just going to be doing calculus in 3 dimensions. So if I call this point P, we say that it is an element of R3, okay? And R3 is defined as the set of all coordinate triples, X, Y, Z, an element of R3, such that X, Y, Z are an element of R. Are you guys familiar with this element of notation? Okay. And actually, R3 is defined as this, but also R3 is really equal to the Cartesian product R cross R cross R. Okay? You guys familiar with that? Ma'am, can you see?
Oh, the computer is blocking the camera.
Okay. My students have to be able to see. No computer is getting in the way of doing that. Okay. Maybe I can do this now. And of course, my calibration is now messed up. Okay, how's that?
That's better.
Wonderful. You got to be able to see. Okay. Although this guy, Leonhard Euler, he actually went blind, and he was still one of the best mathematicians in history. So I rescind that statement. You don't got to be able to see. Okay. Now that we've discussed 3-dimensional situations, I'm going to be talking to you about the concept of a projection. Projection. All right. So actually, I wanted to do it here, but you know, it's so cluttered and weird looking. How about I redraw this situation? Here's my x-axis. Here's my y-axis. Here's my z-axis. Here's some point P of x, y, z. All right. Okay. We see it's located here. Now, in 2D world, we call this, you know, just a plane. Any curve can occupy the plane. Okay, but in 3 dimensions, we have a z-axis emanating out towards you. Okay, so there's still this xz plane or yz plane, it doesn't matter. And that's right here. It's this flat surface right here. But now there's 2 more planes. Now we have the zx plane Here's our old familiar XY plane. What's the other plane we get here? Pardon me?
ZY.
ZY. They combine these two letters and it's ZY. The ZY plane. So we get three different planes here. The book kind of describes it as, think about the corner of a wall. Maybe call this the XZ plane. Maybe call that the YZ plane, and the floor would be the XY plane. Okay? I feel like it's a nice description, so I like to talk about it in class. Okay, so now we get to talk about the idea of a projection. I could take this point P and project it onto any of these planes. What is a projection? I haven't defined it yet, okay? Well, a projection of the point P, which this is not necessarily notation that your book utilizes, but it's notation that I have invented and that I will utilize. A projection of the point P onto the XY plane, I'll call it P star of XY, is this point down here. We have forced the point from up there down there. We smashed it down into the floor, the XY plane. So a projection is really taking a point, if it's in three-dimensional space, and making one of its entries equal to 0 if it had non-zero entries here. So look, X, Y, Z, I now removed all of its Z. So this point will have values X, Y, and a 0 here. That's what it means to project. Can everybody see that? Is the computer getting in the way? The monitor? I really can't, I guess I could flatten it out more if required. Let me know. Okay? Maybe from down here it's not possible to see, right? Can you still see from here?
Yeah.
You'd be able to see something here? Okay, good. So now I know what is your range of vision. I've calibrated. That is a projection on the XY. What's a projection on to the XZ?
You make your Y 0.
So project here, project 0. I heard someone say, you make the Y 0. Who here agrees? Who here disagrees? Nobody disagrees. Well, that's good, because that's correct. We'll make the Y 0. So we get an X, a 0, and a Z. Guys seeing that? We smash it into the wall. Okay. Now, a projection onto the YZ plane. Maybe, have it look kind of like that. Make it look all three-dimensionally. So move this out of the way. Let's call this P. Over here, what will it be its values? Very good. Now you get the concept behind projection. Now I assume you have everything necessary to do your homework. There'll be several problems dealing with projections on your homework. Okay. Now, let's talk about the difference we experience when we graph something in R2 versus R3. I'll call this R2 vs R3. Okay. Is everybody done recording this info? And I'll delete this information with regards to the homework to clear up some more real estate. Wonderful. R2 versus R3. 2 dimensions versus 1 dimension. Okay. So in R2, X, Y, we have curves. You guys are used to this. You've been doing this for a while. You've been trained to believe that that's all there is to math. Is not. Math is not only beautiful intrinsically in studying pure math, studying mathematics for the sake of it. No practical purpose is necessary. We study it and explore it just because the human mind is capable, and we will do it because we are capable. We do it because we can. Also, mathematics is also cool because you can apply it to real life, and it has powerful implications. Matter of fact, if it didn't have that, who knows if math would get all the funding it does? Because, well, I'm just going to leave it at that. This is R2. This is R3. And in R3, we can have curves, of course, we can have curves, but we have a new toy to play with called, oh, I don't like it like that. It's called a surface. How about we do this? A surface. Think of that as like a piece of paper. Okay. A piece of paper is a surface in R3. Okay. All right. Well, you know what? How about I put a binder clip here so I'm not dealing with loose sheets of paper. How you doing, Euler? I will surpass you. But you are one of my heroes. I look up to you. Hopefully you're having a good morning. Anyways, where did my chalk go? Underneath my paper here. Now, we have not talked about R2 versus R3 yet. Okay? We have just set it up. So, how we talk about x is equal to 3 in R2. All right, in R2, what does x equal to 3 look like? Where at?
When x is 3.
Yes. 1, 2. Very good. Now, what does it look like in R3? Well, it's kind of cool, really. When we draw out the Z, it's as if something comes out of the board. Furthermore, it's like something goes out into the board. Okay? A full new axis called the Z-axis gets created. So, what would that do to this line here? It just smears it. It smears it as it pulls it out this way to create a plane. And it smears it as it goes into the plane. Creates a plane back there. Yep, it's a pretty sturdy wall. Yep. So, and it creates a plane. So, where does the plane get created? 1, 2. Does it look like a plane to you? I'm doing my best. Give me a break. Sometimes I like to, in my solutions, do this just to make it look like, oh yeah, that plane's in front, but it's translucent. And I can see the coordinate axes through it. And looking through it makes it look like that. And here, now it's sticking out, right? You guys get that? That's kind of what I'll be doing for visual aids. Okay? And I notationally like to do this. I say plus infinity, minus infinity, just to highlight that this plane emanates to all infinity. It's a plane at x equals 3, and it goes out in all directions, but it stays in its zone, okay? It stays a flat sheet in its zone, but it goes out to infinity, okay? And I do not need to state this, but notice that it is parallel to the y z plane, okay? And perpendicular to the xy plane, all right? And it most likely, definitely, 100% will intersect the xz plane at some point, okay? Very good. So this gets smeared, if you will, into this. That's the difference between R2 and R3. This will be a concept that you need to work on and master, because it might show up on some homework and some tests. Now, let's do a really cool example here. Let's talk about the equation in R3. X squared plus y squared is equal to 4. Okay? And in R3, let's compare it to z is equal to 4. Then we will compare it to in R3, x squared plus y squared is equal to 4, and z is equal to 4. Simultaneously. Okay? Over here, what is the equation of?
Circle?
Of radius? Very good. And in R3, this is a circle of radius 2 in R2. In R3, it is a cylinder of radius 2 that emanates to plus and minus infinity. Why? You know, when I was a young little kid, when mathematicians or teachers in my very, very, very poor public education, poor as in fiscally poor and performance poor. I don't mean to bash on those teachers. They don't get paid a lot. But still, I feel a little wronged because when I asked questions when I was a young kid, they would just say, well, that's just because it is. That's it. No justification at all. The area of a triangle is 1/2 base times height. Why? That's just a formula. Why? Don't ask questions. That's just the formula. That's just how it is. Yeah, but where's your justification? How did you prove that? How should I just take your word? Just because you're the instructor? Just because you're the teacher? I just listen to everything you say and not question the logical validity of your statements, the veracity of your assertions? Well, I got sent to the principal's office very often for this kind of rebellious behavior and for fighting with kids and stuff like that, smacking them because they're acting annoying. But I guess to all the other students, I was acting annoying because they don't care. Some of them care, but most of the kids have had that curiosity beat out of them, and that's very bad. In this class and in all classes, you should ask questions and not have your curiosity beat out of you. So here, I'm going to justify why this is no longer just a circle of radius 2, and that it turns into a cylinder. Notice that I have left out some information that is implied. Z is free. Z is a free variable. We don't fix it at any value like we have here. So because of that fact, Z varies. It can be anything. And it takes the circle and smears it, turning it into a cylinder, a cylindrical shell. It's not solid. Cool? Now let's talk about this one. X, Y, Z, 1, 2, 3, 4. Okay? And create a plane. Okay? That's what it looks like in R3, just z equals 4. Now, here comes the fun part. What does the combination of the two look like? What does x squared plus y squared is equal to 4 and z is equal to 4 give us? And who here has like done proofs like in discrete math? Who here has proofs under their belt? A discrete math here? Anybody else do proofs? Okay. Are you just a pure math major? Aha. Okay. That's the difference. Okay. So there's a concept called the intersection. That's when you take and then there's a concept called the union. That's when you take or. Right now, when I say x squared plus y squared is equal to 4 and z is equal to 4, we're taking the intersection of these two mathematical objects, the plane and this cylinder. Okay? So you might think that you would just get 2 points where it intersects there and intersects there. But it doesn't, because what this is actually saying is not necessarily just like the intersection. What it's saying is now we just get this plane here, the intersection of the two. We get a circle of radius is equal to 2 here at 1, 2, 3, 4 on the z-axis. So now you restore your circle that we talked about in R2, that it's in R3 now. It's a circle that's not in just a plane, it's in 3 dimensions. And actually, it does make sense if I draw the plane correctly. Okay? I draw this plane not so accurately. I mean, it's kind of hard to draw in 3 dimensions, but talking it out, I realized that, this plane should really realistically look more like this. Okay? See that? And now it would make sense that if you stuck a cylinder and intersected it with this plane, it would have a cross section, an intersection, if you will, of a circle. So yes, you don't get 2 points. The way I had drawn the plane was incorrect. If you draw the plane slanted, there's nothing up here and there's nothing down here, but the plane is assuming all values. So anything on any point on this plane, I'm kind of going off on a tangent, but I want to just be thorough. Any points on this plane will have arbitrary x, y, and a fixed value of z of 4. So that's why it forms a plane. You can put any number in for x, any number in for y, if it's a real number, and fix the z to 4, you'll create this plane. So this cylinder will intersect this plane, getting us this circle, because it's a cylindrical shell. It's not a solid cylinder. Make sense? Okay. Moving on. Any questions so far? Now let's talk about distance. Who here remembers the distance formula?
Square root of delta x plus delta y.
But that's in R2. For 2 points in R2, let's say P1 and P2, the distance, which we will denote as this, and P1 is defined as x1 comma y1, and P2 is defined as comma x to y2. The distance is, as this young man has indicated, is the quantity x2 minus x1 squared plus y2 minus y1 squared. Why? Where did that come from? Yes! It is an application of the Pythagorean Theorem. To see that, notice that this is x2 minus x1, this piece right here. And notice that this is y2 minus y1, that's this piece here. And notice that this d is the hypotenuse. So we form a right triangle, and d squared was equal to x2 minus x1 quantity squared plus y2 minus y1 quantity squared. That's what d squared equals. So to solve for it, we took the square root of both sides. You technically get a plus or minus here, but we'll take the positive value solution. Then you get this distance formula. What about in 3 dimensions? Well, the distance between a point capital P1 and capital P2, add the z here, this changes to this. Okay. And I would love to prove it to you, and I could prove it to you, but it would chew up a considerable number of minutes. And so I give you my word. I will put the derivation of the proof on YouTube. I have a YouTube channel. It's called Professor Niazi. Subscribe, like, share. I'm trying to build my followers up, my clout, my subscriber count. You know what I'm saying? So whatever you young kids do these days, do it. Subscribe and like and whatnot. Maybe I should have this over here so I can see if the page numbers are. Okay. So that's the 3-dimensional distance formula. We can trivially, compute. What is this stuff here? Oh, okay. All right. We could trivially compute some distances between 2 arbitrary points, and we shall do so just for the sake of good measure. Where did my chalk go? Oh, here. Okay. Yeah, I have some stuff down there, but I'm just going to invent stuff. Let's say P1 is equal to 1, 2, 3. It's faster than looking. Let's say P2 is equal to 3, 4, and 5. Find the distance between P1 and P2 in R3. No, you notice it's R3 because there's a third number associated with the point, right? It's 3-dimensional because we're in Calc 3, baby. Woo! So, this is my first time teaching Calc 3, and I'm really stoked. So, I do not ask you for pardon, but pardon my enthusiasm. This is really fun. So trivially, we apply this formula. X2, 3 minus x1. Oh my gosh, I'm falling asleep here. Don't fall asleep. 4 minus 2 squared plus 5 minus 3 quantity squared. And then you compute it. That's 2 squared, which is 4. That's 2 squared, which is a 4. That's, what was that? Was that a 3? It looks like a 2. That's 2 squared, which is a 4. Thankfully, I'm not very good at arithmetic, which you guys will notice because I'll mess up very simple arithmetic. So be on your toes when I say 3 times 7 is 45 or something like that. Okay? Catch me. All right? So 4 plus 4 plus a 4, that's 8 plus 12, yep, 12. Okay, so that's the distance between them, square root of 12. Does that break down any further? Well, yes. Due to the fundamental theorem of arithmetic, any composite number can be broken down as a unique product of prime numbers. So 12 is really 3 times 4, and that is really 3 times 2 times 2. So now we have our prime factorization. Notice that 2 times 2 is 2 squared. And notice that the radical can distribute across multiplication and division. So square root of 2 squared is, what is it? There you go. So our real distance, when we break it down, is 2 square root of 3. Now, that is so trivial that I need to move on quickly. Let's talk about spheres. Has everybody recorded everything? May I erase? Also, it's going to be on video. That's a great thing. I vibe with writing stuff down because it helps encode it due to long-term potentiation in your neurons. The actual motion of your fingers helps you remember stuff. So feel free to record, but just know if I erase something that you haven't written down yet, it will be recorded. So now I don't got to keep asking you if you've written it down. I'm just going to erase. Okay, let's talk about spheres. I really like spheres. Okay, let's talk about the general education, not general education, general formula. Okay, who remembers the general formula of a circle in R2? That is not the general formula. That is a formula for a circle of radius R and R2. But in general, a circle is x minus h quantity squared plus y minus k quantity squared is equal to r squared, where this circle is centered at h comma k and has a radius r. You guys remember that? Very good. Notice that the circle and the sphere are intimately related, aren't they? How are they related? Get a circle, put an axis through it, a rigid axis. Spin it and put paint on it. You just made a sphere. Does that make sense?
Yeah, I was going to say like cut like
cross sections. Very good. They're all circles of different radii. Where at the first infinitesimal cross section, it's a circle of radius 0, meaning a point. And then you keep getting bigger and bigger and bigger until you go to the equator, which you get the largest radius, and that's the radius that we're talking about when you're talking about cross sections. Correct? It's related that way as well. So the general formula of a sphere centered at H, comma, K, comma, L is just going to be like, oh, that's duh. Because x minus h squared plus y minus k squared plus z minus what squared is equal to r squared? Huh?
L.
Huh?
L.
There we go. Yeah. We just add that component squared. It turns into a sphere. Mathematically, this is how you algebraically represent what I just said. You stick a rigid axis through the circle and spin it around, put some paint on it. You create a sphere of the same radius. So yeah, you know, this begs us to draw a picture. There you go, here's your sphere. Centered at the origin. So this sphere centered at the origin of radius r would have x squared plus y squared plus z squared is equal to r squared. But if I were to pick this sphere up and move it wherever its new center is at now, we plug it into this formula. So, Dr. Fauci gonna be mad at me. Can't do nothing to me, Dr. Fauci. Yeah, I'm saying that on camera. No one, it's not you. Don't take it personal. Nobody could do anything to me. I'm invincible. I'm unstoppable. I'm quite the rebellious fella. So, not asking for pardon, but pardon my rebelliousness. Let's say we have let's say we have x squared plus y squared plus z squared plus 6x minus 12y. I would have invented this, but sometimes when you invent problems on the fly, it kind of, you might make some issues. So I'm gonna write this one down that I made up. So let's say we have this situation. What kind of surface in R3 does this make? A weird one. It's not that weird. It makes a sphere. How do I know that? Because I've completed the problem and you guys have just been introduced to the beginning. Let us get to that. Why does this make a sphere? What we will do is complete the square in the variables x, y, and z. You guys remember completing the square? Yeah, I have. If you don't, I have videos on completion of the square on YouTube. Look them up. So what we'll do is we'll combine the terms x squared plus 6x, y squared minus 12y, z squared plus 4z equaling r0. And I've suggestively put a space between them for the additive term after completion of the square. We'll complete the square in the variable x. We get b divided by 2 and squared. This becomes 3 squared, which is 9. So I add this piece here, and I will add this piece here. Then we'll complete the square in the variable y. Notice that we get negative 12 divided by 2 and squared. It becomes negative 6 squared. And then we get 36. So I add this piece here, and whatever you do to one side, you gotta do to the other. Then we'll complete the square in the variable z. We get 4 divided by 2, quantity squared. So I get 2 squared is equal to 4. Add a 4 here, add a 4 here. Now, beautifully, because we've completed the square, we can factor this. You know what? I don't like people telling me what to do. Can you remove your mask when you're drinking stuff? Goodness gracious. I gotta drink some water. I got some chalk up in there. There we go. I must have breathed in some chalk because there's something in the back. So, okay. Now, beautifully, we can factor. All right? And the completion of the square tells us what the terms are. So we get x plus 3 quantity squared plus y minus a 6 quantity squared plus a z plus a 2 quantity squared is equal to 9 plus 36 plus 4. Combine those two, we get 40, it becomes 49. And 49, oh, I know this one. It equals 7 squared. Aha! This is a sphere. Is it not? What is its radius?
7.
Correct. Where is it centered at? Give me all three numbers for its location. 3, negative 6, 2.
Negative 3.
Aha! Where did I delete the general formula? No, I didn't. Yes.
You're right.
Yeah, I am. Yeah. There's a reason I'm up here teaching, maybe. I don't know. But I can be wrong. So just because I'm up here does not mean I have it all figured out. Make sure you question me. Make sure you double check me. And make sure if you have a question, ask your question. Because this is my humble opinion, that there's no such thing as a stupid question. The fact that you are questioning implies that you have intellect. Yes. So there is no such thing as a stupid question. Ask away. So, as you caught yourself, young man, you notice that this should say negative 3, because somehow the negatives in the standard formula must have canceled. And then we put a comma here. Oh, that must be a what? Positive 6, right? Because there was no cancellation in the standard form. And then over here, we got a positive 2. So this entry is a what? Negative 2. So this is a sphere of radius 7 centered at negative 3, 6, negative 2. How am I doing on time? Oh, class has been over for 3 minutes. Get out of here. Oh, and you guys know the homework problems. Work on your homework immediately.
Did you say when it was due?
It'll be due a week from today.
Okay.
I expect the most amount of dedication and hard work from you all.
Did you already explain to them what's happening with that?
Yes.
Okay.